Hello. This will be a demonstration of Proposition 7 from Book 10 of Euclid's Elements, which says that magnitudes which are incommensurable with one another are not to each other as a number is to a number. That is to say, incommensurable magnitudes, the ratio of incommensurable magnitudes, is not the same as any ratio of two numbers. All we're given are two incommensurable magnitudes, A and B. And what we want to prove is that the ratio which A has to B is not the same as any ratio which a number has to another number. For if this is not the case, then A will be to B just as a number is to a number. But we know from Proposition 10.6 that if a magnitude is to another magnitude, just as a number is to another number, those two magnitudes are commensurable with one another. So that if we say that A is to B just as a number is to a number, it therefore follows from Proposition 10.6 that A is commensurable with B. But this is contrary to what we were given, for we were given that A and B are incommensurable. And so we have to say that A is both incommensurable with B and commensurable with B. This is obviously impossible, and so we can conclude that A has not to be the ratio which a number has to a number, that there are no two numbers which have to one another the same ratio which A has to B. Now this is what we set out to prove, so we are therefore done with the proposition, therefore etc. QED. Straightforward contrapositive as always. We've seen this plenty of times by now, so this sort of logic should be second nature, or at least it is to me. Just to give an example before I close out the video, say we have the classic example of a square, and we know that the side of a square is incommensurable with its diagonal. Say we know this right off the bat. So say we have A, B, and then we have C up here. I won't bother writing up the fourth point. And say we know that AB is incommensurable with AC. Say we know this. Then what follows is that the ratio which A has to B, or AB has to AC, which the side has to the diagonal, is not the same as any ratio which a number has to a number. This would just be a concrete example of what this would look like. If we were to put numbers to this, for example, or numbers, not in the Euclidean sense, but in the more modern sense, we would say, for example, if AB is 1, then AC is the square root of 2. And if we know that 1 and root 2 are incommensurable with one another, then we can say that the ratio which root 2 has to 1 is not the same as any ratio which a number has to a number. Or put more simply, because this is 1, we can just get rid of it and say that we cannot represent root 2 as a fraction of two numbers. Like that. There are plenty of videos on YouTube going through this proof. It's in fact, I think, one of the most famous proofs in all of mathematics, the irrationality of the square root of 2. Of course, I mean irrationality in the more conventional sense, not in the sense that Euclid is going to use it throughout Book 10. But this is just an example of what this proposition might look like. So the side of a square is incommensurable with its diagonal, but we get that root 2 is an irrational number. We cannot represent it as a fraction or a ratio of two numbers. That's all I've got to say about this proposition, so I'll end the video here and move on to Proposition 10.8.